All right. One of the things we've been asked is, can transformed polynomials be even, and if they could be odd? So the question is sort of, it depends on the transformation. If we have stretches or compressions, then yes, they can be either. They can be even or odd, because that just compares how much they've squished towards or away from the x or y axis. But translations away from the origin prevent even or odd from being an option, because they make it impossible for that polynomial to either be reflected across the y-axis and have nothing happen, or for that polynomial to be spun around the origin 180 degrees and have it look like nothing happened. Next, we're looking at specifically the concept of power functions. And this is really just a very tiny subgroup within polynomial functions. So polynomial functions, power functions are polynomials that only have a power. They can even actually not be polynomials in that their powers can be something other than an integer, and that actually takes us into some other families. So power functions are kind of a strange group of functions because they actually bridge a couple of different families. So first of all, what is the difference between an exponential function and a power function? Well, in an exponential function, you would have something like y equals b to the x, where x is in the power. X is the exponent. Whereas in a power function, you would have something like y equals x to the b, where x is the base. So exponential functions are a completely different family of functions that do not follow the patterns of power functions. Power functions, your x is your base and your power is a constant. Within this, we have something called the constant of proportionality, and that's the number that I actually didn't bother to write in 5a. I could have written y equals a x to the b, and then a would be that constant of proportionality. So it's the same vertical stretch, vertical compression that we've seen in lots of other functions. In 5b, we're going to actually make use of the power function. We're going to have a wind turbine, which generates 1,200 kilowatts of power in a 20 mile per hour wind. And we're asked, how much power does this turbine generate in a 12 mile per hour wind? So obviously we would expect it to be less, but the question is how much less? So it says use the formula for P as a power function of velocity. So they give us the power function to work with. So P is power and V is velocity. So we start with a pair of information that we know. We know that a power of 1,200 watts can be generated in a velocity of 20 miles per hour. So if I think of 2 cubed as being 8, then 20 cubed would have to be 8,000. So I have 1,200 equals 8,000 A. And if I want A alone, I'm going to divide both sides by 8,000. The first thing I see is that 2 of those zeros, I can just reduce that fraction by 100. And that 12 and 80 are both divisible by 4. So if I divide each of those by 4, I end up with 3 over 20 as my A value, right? 12 divided by 4 is 3, and 80 divided by 4 is 20. Now that I know my A value, I can modify this by substituting in the actual value. I know that the constant of proportionality is actually 3/20. So now I have a complete model for this particular wind turbine. Given that, I can take my 12 mile per hour wind and substitute it in for velocity. So I can find out that the power generated in a 12 mile per hour wind just involves a little bit of arithmetic here. So doing that out, I'll get an approximate value of 259.2 kilowatts being generated in a 12 mile per hour wind.